Okay, well, thank you everyone for coming again to another ONEPAS Thematic Series. Actually, this is our last one of the thematic series on steady water waves, and we're very pleased to have with us Erik Wahlén from Lund University. And as you can see, he'll be talking about three-dimensional steady water waves. Erik?
Thank you, Ian, and thanks to all the other organizers, so Benoit, Fabio, Javi, and especially to Walter for setting up a very nice seminar series. Yeah, so it's 9 o'clock here, so unfortunately I've had to see most of them on YouTube, but I really enjoyed the talks. Okay, so yeah, so as I remarked previously, the title was actually supposed to be three-dimensional steady water waves. I forgot to remove the with vorticity. So most of it's going to be about the irrotational problem, and then there will be something about vorticity in the end. And I think I've been way too ambitious with the number of slides, but we'll see. Okay, so okay, so most of the talks have been about this, right? 2D water waves. Even here you see some three-dimensional effects. But so I thought it'd be nice to end with something about 3D theory. And so there's considerably less done in 3D for, well, we'll see, touch upon some of the reasons why in the talk. But here you see some types of, well, both of these are doubly periodic waves, and so you can see them both in the lab and in the ocean. And I apologize for being terrible at giving credit in the photos, but yeah. So okay, so I think a large part will be about doubly periodic waves or biperiodic waves, but I'll also say something about other types of waves, especially solitary waves. Okay, and you've all seen this before, but it's good to repeat it just so that we get the notation straight. So I'll consider just one layer of water, and it will be, I think all of this will be in finite depth with a flat bottom. And there will be gravity, and in large parts of the talk also surface tension, so that will be very important in 3D. Okay, so but the underlying equations are, like in most of the other talks, the Euler equations. Yeah, and as in the other talks, I will be concentrating on the steady problem. Density, I've set density equal to 1 here in contrast to last week. And okay, so maybe for the notation, I'm using the letter H too much, so I had to have mathcal H for the curvature. So these are the usual, I'll repeat them here. So we have the Euler equations, incompressibility, and then the usual boundary conditions, which are the kinematic boundary conditions on the top, on the surface, which means no fluid penetrates the bed, and also that the surface is moving with the water. And then we have the dynamic boundary condition saying that the jump in the pressure from the air region into the water is proportional to the mean curvature. Okay, yeah, so and some notation, I'll use capital boldface X for the horizontal variables X and Y, and then Z is the vertical. Okay, so we'll consider steady waves for the rest of the talk. And for the most part, traveling in the X direction. So then, well, by making this going to a moving frame and making this change of variables, we then get essentially the stationary version of the problem instead. And in this domain, we're bounded above by the free surface eta. Okay, so, right, so in most of the talks so far, we've been in 2D, so then you can use the stream function formulation. Or in the irrotational case, velocity potential. But let me say something in general. So, so vorticity, as you saw it already in the title, will be important. So the vorticity is defined as the curl of the velocity. Sam talked a little bit about vorticity last time, and so in contrast to last week, the vorticity will, in general, in 3 dimensions, it's a vector, not a scalar. So, and then in the vorticity equation, you have now the right-hand side. Even if the density is constant, you don't have 0 in the right-hand side. So in general, the vorticity is not constant along streamlines. Okay, so this is one way sort of rewriting the Euler equation. So you have this sort of transport-like equation for the vorticity, and then you can recover the vorticity, the velocity field from the vorticity using some elliptic problem. Okay, so that's one way. Another way is actually to reformulate it in terms of Bernoulli's equation. So you can understand Bernoulli's equation in different ways. So, from the Euler equations, if you simply take the curl of both sides, then you get this relation. And you can also go the other way around. So starting by assuming that u cross the vorticity, so the velocity field time across the vorticity is the gradient of some function, then you actually recover the Euler equations if you define the pressure so that this holds. So this function h will be, I call it the Bernoulli function. This will be important at the end of the talk. Okay, so so one way of satisfying these equations is actually to assume that the vorticity is everywhere 0. Then trivially, this equation, the vorticity equation, is satisfied, as is Bernoulli's equation with right-hand side. So the Bernoulli function then will be constant. So this is what I'll start with, the irrotational theory. So then the Bernoulli function is just constant everywhere in the fluid. Okay, and so as you are probably all familiar with, then you can introduce a velocity potential. So the curl is 0, so u is the gradient of some function. And here I've written it in this way. I mean, you could incorporate this term into the potential phi, but then, so in general, for example, if you are looking for solitary waves, then you want sort of the gradient of phi to, so this phi gradient will go to 0 at infinity. Okay. So formulated in terms of the velocity potential, we just get Laplace of phi is equal to 0. And then in addition, we have, so this is, you could replace, so these two, the last two equations, these are just the kinematic boundary conditions. And then this boundary condition is, so this is essentially the dynamic boundary condition where we've substituted in this expression for the pressure and eliminated a constant. So you can, by redefining phi, you can swallow this constant. Okay. So, yeah, so one way, so we still have a free boundary problem, meaning that we don't know the domain, so we have to find the domain as part of the problem. So one way of sort of eliminating the problem with phi being defined on an unknown domain and so on is to reduce everything to the boundary. And so this can be done using, since we have a linear equation for phi, just Laplace's equation, we can reformulate it like this. So here capital phi is now the trace of the velocity potential on the surface. And then, so if we go back, so we defined the Dirichlet-Neumann operator as the linear operator, which takes the Dirichlet boundary data of this velocity potential phi to the Neumann data on the surface. So, and here I should say this is not the normal derivative, but it's convenient in the water wave problem to take this non-normalized normal vector. Okay, so if you don't look at this equation, it's just what I had on the previous slide, reformulated in terms of the Dirichlet-Neumann operator. What is slightly more or less trivial is this reformulation of the dynamic or Bernoulli condition on the surface. So you can express everything on the surface in terms of the Dirichlet-Neumann operator, which is essentially the derivative in a normal direction, and the other things are just derivatives in the tangential directions. So if you play around with it, you get this expression. Okay, so as I promised you, I'll start by talking about doubly periodic waves or biperiodic waves. So this is the sort of natural analog of the Stokes waves, which we have in the 2D problem. And so there's some of the easiest solutions to look at because you have a compact domain. Okay, so now we assume periodicity in two different linearly independent directions, so lambda 1 and lambda 2. So lambda 1 and lambda 2 generate the periodic lattice. And then in general, so if you have biperiodic functions, then you can express them in a Fourier series like this, where the wave vectors k lie in the dual lattice, so generated by two linearly independent vectors satisfying this relation. Okay, so I just thought it might be nice to include an example of what this might look like. So if we have this symmetric situation, which will be important in the coming slides, then so the dual lattice will then also be symmetric. So here I have kind of reflection symmetry with respect to the x-axis. Okay, so right, so now we do the usual thing when we look for small amplitude periodic solutions. We linearize the equations and then, well, see what solutions we get then. So if you linearize, then you get these two equations, and where now this is the Dirichlet-Neumann operator corresponding to a flat surface. So, and this is most easily understood, I think, in terms of the Fourier transform. So if you take the Fourier so this is just the Fourier multiplier operator with this symbol. Okay, so we've seen this before. I mean, if you can almost think of it as being multiplication with modulus of k, because, well, I mean, for large k, this is exponentially close to 1. Okay, so these are the equations, and then if you look for solutions, well, so of cosine or sine type, then this leads to this dispersion relation. Okay, so this gives you the condition for finding a doubly periodic traveling wave solution to the linearized problem. Okay, so to understand this dispersion relation, I thought maybe it's best to look in the at contour plots. So there is a problem here. If you express c, the wave speed, as a function of the wave vector, then actually this function has a singularity at the origin, because here you're dividing by k1 squared. Okay, so this is not. So I mean, in one dimension or in 2 dimensions, it's not a problem, because then here altogether so the hyperbolic tangent also gives you another mod k. So in 2D, these two essentially cancel at the origin, so that the function is regular. But in the 3D problem, you have the singularity. Okay, so there are essentially two different cases if you include surface tension. So these are distinguished by the size of the bond number. So the bond number is a non-dimensional version of the surface tension coefficient. So in the case of strong surface tension, all of these level curves connect to the origin, whereas in the case of weak surface tension, they do not. So maybe if you're familiar with a 2D problem, the way to think about this is to look at the K1 axis. So if you think about the strong surface tension case, then essentially what you see is that the wave speed as a function of the wave number is a monotonically increasing function. And so you would, for each C, you only get one intersection. Whereas in the weak surface tension case, it will first go down and then up. So for each value of c, you get, well, you can get, if you go far away, you can get more, just one intersection. But if you're sort of in the subcritical case, then you will get two intersections. And then these contour plots show how things look away from the K1 axis. Okay. Right, so then you can get doubly periodic solutions to the linearized problem essentially just by picking, for a given C, you just pick two different linearly independent wave vectors or points on these dispersion curves. Okay, so, right, so let me tell you a little bit about the existence theory for gravity capillary waves. So both with gravity and surface tension. So I think there have been, at least for the, okay, so for the, in the pure gravity problem, I know that there are sort of former results doing sort of Stokes type expansions, at least going back to the 50s. But the first rigorous existence results for the full water wave problem are, well, is this result by Reader and Schimbrot. So they constructed symmetric diamond waves, which, so corresponding to the lattice I showed you before, where you have this sort of symmetry, reflection symmetry in the K1 axis. And you also assume, well, so if you have the symmetry of the fundamental domain, then you can also assume symmetry of the surface. So symmetry in both X and Y. And then choosing, so what this does for you is that it reduces sort of the dimension of the kernel. So remember, if we go back to this curve, so I mean, essentially what you want is to have sort of two different intersections. Well, you want two different points here. So intersections with the lattice, if you want. Well, if you have that, then you will automatically have intersections over here. So that immediately gives you a four-dimensional kernel. So what these two symmetries do for you is that they allow you to reduce so that you just have a one-dimensional kernel. And then you can use bifurcation from a simple eigenvalue. So this is essentially what Reader and Schimbrot did, although they formulated it slightly differently. Okay, so I mean, it's not always the case that the kernel is just one-dimensional. So you have to choose the parameters carefully so that this is the case. So Reader and Schimbrot had to avoid certain parameters where you have a higher dimensional kernel. And in particular, they they remarked that there are problems with setting sigma equal to 0, so considering the pure gravity case. Okay, so then the next sort of fundamental breakthrough is Craig and Nichols, who considered an arbitrary fundamental domain, so without assuming any symmetry. Okay, so you still actually you always have a symmetry if you consider X and Y together. So sort of symmetry in you do reflection in the origin instead. So you can still do this to reduce the kernel to 2 dimensions. But to get interesting waves, you have to assume that it's, so to get waves which vary in 2 different directions, you have to assume that it's at least 2-dimensional. Okay, so, well, so one trick you can do then is to actually use 2 different bifurcation parameters. So if you allow, instead of having the wave vector being just aligned with the horizontal axis, you allow it to be general and to vary in sort of in both directions. And now you have 2 parameters, and then you can do sort of bifurcation from a double eigenvalue. And this, so instead of having a curve of solutions bifurcating off, you get a surface, a bifurcation surface. So this is what you can do to handle this case. So actually this is not quite what Craig and Nichols did. They did something more elaborate, namely they used a variational formulation of the problem. So it turns out that traveling waves are critical points of the energy, subject to the constraint, to 2 constraints. So you have you constrain the horizontal momentum, and there are two components of the horizontal momentum, one for each, one in the x direction and one in the y direction. So this comes from the Hamiltonian formulation of the problem. So this is actually the conserved energy, and the momentum is also conserved due to, so this is due to translation invariance in the x and y direction. And so your wave vector c will then appear as a Lagrange multiplier. Okay, so this is very nice, but this variational functional is sort of hopeless to work with if you just try to do something directly with it. So it's definitely not coercive or anything. So what Craig and Nichols did was to use a variational Lyapunov-Schmidt reduction. So you do Lyapunov-Schmidt reduction, but if your original problem is variational, then the reduced problem will also have be of variational form. So now you have sort of, now you're in a four-dimensional setting, and you have sort of an optimization problem in four dimensions. So, okay, so there's some hope of doing something. And actually you could do a bit more. So you can also use this translation invariance, which I mentioned before. So this gives an invariance under what they call a torus action. So that's just a fancy way of saying that you sort of, okay, so you have translation invariance, but due to the fact that we're assuming periodic boundary conditions, we can essentially identify this translation with living on a torus. Okay, so if you do that, it turns out that in the end, well, so this means that, well, okay, so they do that, and they also use these, so you still have a constrained variational problem. So you essentially, these constraints, they will reduce the dimension to 2 essentially. And then if you also use the torus action, it means that your reduced function is actually constant. So you automatically get a solution, a trivial solution to the optimization problem. So this gives you a 2-parameter family of solutions indexed by these 2 constants, the momenta in the 2 different horizontal directions. And this works whenever A is not collinear with the wave vectors k1 and k2. So you have to avoid some cases. Okay, right, so, and they do something more as well. So they also are able to say something about the case when the dimension of the kernel is higher. So if the sort of even dimension of the kernel, so ignoring the fact that you can have both cosine and sine, this is n, so the total dimension is 2n, then you can use this to produce at least n-1 geometrically distinct solutions. Okay, so yeah, so there is a topological argument to do this. So at least it matches with the case we had before. So when the dimension is 2, so then you get at least 1 geometrically distinct solution. And then okay, so the 2-parameter family was because you could vary the constraint surfaces. Okay, so now I want to say something about gravity waves. So with still restricting to the doubly periodic situation. So why is it? Why was it important to include surface tension so far? Well, so this in 2 dimensions there is a lot of theory for gravity waves, which we've already heard about. So the problem in 3 dimensions is that you run into small divisor problems. So sort of the problem if you reduce to the boundary is not elliptic, whereas it is in the if you include surface tension or if you're in 2 dimensions. So you can see this by looking at, so this is sort of what I had in the dispersion relation, but now I've removed the surface tension term. And so now for large K, I said that you can essentially ignore this hyperbolic tangent, and then you get something looking like this. And okay, so you can do some further reduction to even more clearly see that this can be small, or at least not the size of the order of the symbol for large values of the wave number. So we get infinitely many wave, well, size on your lattice where this is small. And so you cannot hope to sort of invert this operator without losing derivatives. Okay, so that tells you that you shouldn't expect to be able to do some standard bifurcation argument. You have to do something more, much more elaborate. So in spite of these difficulties, Jos and Plotnikov, in their two seminal works, managed to prove the existence of a large family of solutions using Nash-Moser iteration. So here's not, as is typical for Nash-Moser iteration, you don't get sort of connected family. You have to remove parameter values. So you get sort of these Cantor-like sets. So there are two papers. I think I only included one in the reference list, so I thought this was substantial enough to start with. So first there's the symmetric case. So it's sort of the analog of what Reeder and Schimbrot did, but without surface tension. And then there's the analog of the Craig and Nichols paper, so for general fundamental domains. Okay, so, right, so now let me turn back to surface tension and mention a completely different method, which we heard Miles mentioned 2 weeks ago, so namely spatial dynamics. So this is another very useful method for constructing solutions, and this has been used a lot in the 3D case. So Miles mentioned that it's been used, you can use it, it's very useful also in the 2D problem even, but I think it's even more useful in 3D. So the idea is essentially to write the equations so you formulate them as a sort of evolution problem where an unbounded horizontal variable plays the role of time. So, okay, so first of all, you have to, as always, we have the problem with the free boundary. So technically, we first flatten the domain. So we will get the problem, sort of an elliptic problem where the surface eta appears as, well, it appears as a coefficient. Eta and its derivatives appear as coefficients everywhere. And so you have to work a bit, but you can formulate this as a first order in C evolution problem. So where the right-hand side here, so L is supposed to represent a linear operator and N some nonlinearity. So this will typically also involve, this is really an operator, it's not a matrix. I mean, this will involve derivatives not in a C variable, but in the vertical variable Z, and then in another horizontal variable Y. Okay, so the advantage in 3D is that C can be a general horizontal variable. It doesn't necessarily have to be aligned with the direction of propagation. So it doesn't have to be the x-axis. And again, and then Y is just some other horizontal variable. Okay, so the problem, if you do this, is that typically this problem is going to be ill-posed. But there is still some hope, namely, if the number of eigenvalues on the imaginary axis is finite, and the rest of the spectrum is separated from the imaginary axis, sort of like this, then you can apply a version of the center manifold theorem, which reduces the problem to a finite dimensional problem. And then for this finite dimensional problem, you can use all your favorite techniques from dynamical systems. Okay, so, right, so in order to have this nice situation, you essentially need some form of compactness in the Y direction. Otherwise, you will generate essential spectrum close to the imaginary axis. So essentially, this requires periodicity in the Y direction. Okay, but still, you have this other direction to play with. So the behavior in the C direction, the evolution direction is, so you're free to choose this as you like. And so in particular, you can construct doubly periodic waves. So this was first done by Groves and Mielke around the same time as Craig and Nichols. So they considered a symmetric case again, like in Reeder and Schimbrot. So essentially okay, so I should explain this picture as well. So here you have your doubly periodic wave. And what happens is that in the x direction, so this is your sort of reduced dynamical system where you have a closed orbit. And this will, in the x direction, this will generate a periodic wave. And then also in the y direction, you have periodic behaviors. So then you will get something which looks like this. Okay, so Groves and Milka did the symmetric case with c being equal to x and capital Y being just the orthogonal direction. And then Groves and Hargus later did consider the asymmetric case. So like in the Craig and Nichols paper where you can have an arbitrary fundamental domain. Okay, so this is one thing you can do with spatial dynamics, but like I said, you're free to choose the behavior in C more or less like as you like. Well, okay, so it has to, of course, come from the behavior of your reduced dynamical system. But that reduced dynamical system in this situation can actually have more or less arbitrary dimension or arbitrary many degrees of freedom. So that is in contrast to the 2D problem. So essentially you can find, I mean, if you think of sort of any type of behavior in, well, let's say conservative and reversible finite dimensional dynamical systems, then you can get that type of behavior here. So some of the type of waves you can find are, you can find these waves which are periodic in the y direction still, but localized or solitary in the x direction. So that would correspond to a Hove-Klinic orbit in the reduced dynamics. And you could get, for example, generalized solitary waves. So these are, if you have a sort of a Hove-Klinic orbit or to a closed orbit or heteroclinic orbit between two different ones. But you can also get many other types of waves. So you can get you can get waves which have are multi-humped, so more complicated homoclinic orbits. You can also get solutions which are quasi-periodic in the x direction. And then you can also play around with the angle between these two different directions. So I included one sort of an overview paper by Mark Groves, which is a good introduction, I think, where you can read about all these types of different behaviors. Okay, so one thing which is difficult to do using spatial dynamics, which I think was touched upon 2 weeks ago, was to get fully localized waves. So you can do spatial dynamics for sort of waves which are localized in all horizontal directions, but I've seen this done for problems where you have radial symmetry, and this you don't have in the water wave problem. So there are a number of papers by Arnold and collaborators on this subject. So one problem where this actually seems to work is if you instead consider ferrofluids, because there you're actually considering a truly stationary problem, so not a traveling wave, but a stationary problem. And so for that problem, there is hope of actually finding radial solutions using spatial dynamics in the radial direction. Okay, so before moving on to fully localized solitary waves, I wanted to say something about some open problems and something about, well, so this will mostly be about moderate or large amplitude solutions. So what I've said so far, I've sort of, maybe I didn't say it very clearly, but this has sort of all been for small amplitude solutions. So far there are very few results on large amplitude or moderate amplitude solutions, but there's of course a lot of numerics. So even numerically, this is difficult. I mean, simply, if you add a dimension, things become more complicated. So one interesting thing that you see if you go to higher amplitude, so this is from a paper by Craig and Nichols for the pure gravity case. So one thing you see is marked depth dependence. So on the left, we have shallow water, and to the right, deep water. And deep water, it means it doesn't have to be very deep. So as soon as it's not very shallow, you see this effect. So if you look at, so these are all waves with sort of a large aspect ratio. So this is, oh, I forgot, I removed the labels on the axis. But so the waves are traveling in the horizontal direction. So that's the x direction, and this is the vertical. So these waves are all sort of, so the distance between successive crests is small, so in the x direction, and then so they're elongated in the transverse direction. And as you can see, in shallow water, you get this kind of hexagons, whereas in deep water, you get sort of this rectangular type shape. So this is very interesting. And you can sort of connect this to model equations, namely the KP equation for shallow water. And so I think these can be modeled by NLS, some version of NLS. Okay, and I also included another picture from the Craig and Nichols paper. So these were contour plots, and these are plots of the actual surface. Okay, so these are numerical works proving anything, I mean, in this direction. So with large amplitude would be very interesting. And so for gravity waves, one particularly interesting question is, of course, what type of singularities you can get. So, I mean, you expect, like in the 2D problem, to get that there should be waves which are not smooth, that they have some sort of singularity, but I think very little has been done on this subject. Okay, so I mean, it's not clear even geometrically what this will look like. Okay, so another thing you could look at is if you include surface tension, then we of course expect to get, so that the large amplitude behavior should be different, and that you should be able to get overhanging waves. So there have been some nice recent numerical progress on this by Akers and Rieger. So they used sort of, well, boundary integral methods to produce these type of waves. So I think what they do is essentially that they start with something like Crapper's waves, which we heard Vera talk about, and then they do sort of dimension break and bifurcation. So they add sort of weak variation in the transverse direction. So, and again, proving something rigorously about this would be very interesting. So there are essentially no global bifurcation, even sort of abstract global bifurcation results for this case, as far as I know. Okay, so I think this was what I wanted to say so far about doubly periodic waves. Maybe I'll return to doubly periodic waves at the end and say something about vorticity. But first, I wanted to say something about fully localized waves, because this is sort of one of the things I've been working on in the irrotational problem. So again, first, before going to surface tension, let me say something about the gravity case. So then there is a non-existence result by Walter Craig saying that there are no fully localized solitary waves with constant sign in 3 dimensions. So sort of in 2D, well, I think we've heard Miles talk about this. So in 2 dimensions, you kind of have this sign condition. So maybe this is now even totally complete, but at least the waves we know of have a strict sign. So it could be that there are some solutions in 3D without surface tension, but they would then necessarily have to change sign. Okay, so then to get some sort of positive results, I will now let sigma be positive. And okay, so in order to explain, so there are sort of essentially 2 different results I will talk about. And again, this has to do with the size of the bond number, so weak or strong surface tension. And to explain the difference here, we look at model equations. So there are 2 model equations I will mention. So one is the KP equation. So this is a model equation which works for all values of the bond number. But so what you assume is essentially that you have long waves, and then sort of the scaling is even longer in the transverse direction, and small amplitude, of course. So this is like a 2D version of the KdV equation. And so you can derive this for all values of beta, but in particular, if beta is greater than 1/3, so this is the KP1 equation, then the KP equation is known to have a fully localized solitary wave. So this looks like this sort of upside down sombrero. Okay, so this, so it's not the typical wave that you see in the ocean, but nevertheless, this is a solution to the KP equation. Okay, so then you could, so for weak surface tension, the KP equation is, there are no known fully localized solutions. Okay, so this is for weak surface tension, strong surface tension, and then a natural question is if there is an analog of this in a full water wave problem. Okay, so the other model equation is the Davis-Stewartson system, which you should think about as a 2D version of the NLS equation. So essentially then you assume that the main part of the wave is sort of just a plane wave moving in the x direction, small amplitude, and then it's sort of modulated by this amplitude, zeta. So zeta will be a decaying modulation. So this, so the Davis-Stewartson equation, so it's actually slightly simpler if you go to infinite depth. So then you just get the 2D NLS equation. Okay, so the Davis-Stewartson system is known to have localized standing wave solutions if all of these coefficients are positive, and you can get them by variational methods. So, right, so one difference, so for KP, you can actually find an explicit fully localized solution, whereas for Davis-Stewartson, you have to prove it using some indirect methods, so for example, variational methods. Okay, so these, even if they are standing wave solutions to the Davis-Stewartson system, they correspond in certain cases to traveling waves of the water wave problem. So this is if the, okay, I didn't explain what these are. So this is the phase velocity or phase speed, and this is the group speed. So in general, the speed of the envelope doesn't have to be the same as the speed of the carrier wave. But if the wave number is between 0 and 1, sorry, if the bond number is between 0 and 1/3, and you choose a particular version of the wave vector, then you can get these two to be equal, and then you get the traveling wave solution. Okay, so now again, we ask the question whether there is an analog of this solution for the full water wave problem. And so one way of proving this is to use variational methods. So this connects to the Craig and Nichols paper. So again, we use this is the modified energy where we subtract c minus the horizontal momentum in the x direction. So now I just include one of these two momenta because I want the waves to be traveling in the x direction. Okay, so now I look at this functional, so instead of sort of fixing or constraining the momentum, I just look at this variational function directly. Okay, so again, there are huge problems with attacking this directly. So what we'll do is something similar to Craig and Nichols, namely, so they used the variational Lyapunov-Schmidt reduction. So the idea here will be to do something similar. We will reduce to another functional. And again, so we reduce the dimension by looking sort of close to the wave numbers we're interested in. And we get a reduced variational functional, which is easier to handle. So in Craig and Nichols, they get a finite dimensional problem. Here we still get an infinite dimensional problem, but it's simpler to deal with. Okay, so this variational reduction works like follows. So we work with wave, the wave speed is close to sort of the critical wave speed, which comes from well, where these bifurcate from. So this is sort of the minimum of the dispersion function. So first we do one thing first, namely to eliminate the velocity potential. So this is sort of an easy thing to do because things are sort of, this is just a quadratic problem in the velocity potential, or sorry, this is actually the trace of the velocity potential to the surface. So that's relatively easy to get rid of. The problem is coercive in that direction. Okay, and then we get the problem formulated just in terms of the surface, which looks like this. So you have two different functionals, k and l. So this is a bit confusing, but the first one comes sort of from the kinetic energy and the second one sort of from the potential energy. Okay, so this is still a hard functional to work with. And now we do the main step of the reduction. So the idea is, instead of doing a sort of, well, it's like a Lyapunov-Schmidt reduction, but it's not, we don't use the kernel of sort of the linearized problem. So what we do is somehow if it were sort of the kernel, we would just sort of look at directly at these points, these wave points in the sort of, so in the K space. But what we do is we allow some freedom. So we localize in Fourier space around these interesting wave vectors where we have the bifurcation from. So chi is the characteristic function of these sets. So you should, if you remember what the contour plots I drew before, you should sort of think of this as being sort of the level, almost the level curves of the dispersion function. Okay, so we split eta according to this. So we have, so eta 1 is the part which lives close to k0 and minus k0, and then eta 2 is the remainder. And then we split the Euler-Lagrange equations accordingly. And so we solve, this part is actually easy to solve because we're sort of far away from criticality. So so you can use an implicit function argument to solve that part. And then you plug this part, so eta 2, solve eta 2 for eta 1 and plug that into the first equation. And then the reduced functional, then the reduced problem turns out again to be variational and correspond to this variational functional. Okay, so I'll try to, since I'm running out of time, I'll just do this quickly. So the idea then is that this reduced functional is much easier to handle, and using some further change of variables, you can reduce this to a perturbation of the Davis-Stewerson functional, which Cipollati used to prove the existence of a fully localized solitary wave of the Davis-Stewerson equation. And so then the trick is just to show that this perturbation doesn't interfere too much. Okay, so maybe I'll just quickly go through, say something about strong surface tension. So you can play the same game there. It's just that this, so I said that there is an explicit solution to the KP1 equation. So actually that's not what we do here. I mean, so you could use that and try to do an implicit function theorem argument. Another way is actually to use this variational method again. So there is a proof of existence of fully localized solutions to KP1 by Debord and so. So they use this variational functional. And so again, use this variational reduction, but with now a slightly different splitting, which corresponds again to sort of, it's similar to the level, so these contour plots I showed before for the dispersion relation, but in the strong surface tension case. So you get this kind of bow tie set. And if you then use similar arguments, you can reduce to a perturbation of the KP1 functional and show that this also has a critical point. Okay, so I'm not sure if can I continue for 5 minutes or something? Yeah, okay. Okay, so this is still, so the first result is published and the second is work in progress. Okay, maybe I'll skip this. So there, well, okay, let me say, I should say something quickly. So these are not, for the strong surface tension case, these are not the first results. So the first result was by Groves and Sun, where they used a more complicated variational argument. And then there's a result by myself, before Groves and Sun. It's again a more complicated variational existence result, which, however, has the advantage that it also gives stability. So there we minimized, we essentially did something like Craig and Nichols, namely minimizing the energy subject to the constraint of fixed momentum. Okay, so in the final minutes, I'll say something about vorticity. Okay, so first of all, there is an important result in sort of three-dimensional fluids, namely sort of a dichotomy between two different cases. So this is the case of essentially Beltrami flows, where the vorticity is parallel to the velocity, and then the other case where it's not. So in the first case, you see this left-hand side of the Bernoulli equation is 0, and so the Bernoulli function h is constant everywhere. In the other case, I wrote former case here, but what I mean is in the case where they're not parallel, the flow can be chaotic with streamlines dense in open subsets of three-dimensional space. So a classical example of this is the ABC flow, and then there are also some more recent general results. Okay, so the first setting where these are parallel, so Beltrami flows I mentioned, I mean, we have already talked about one case where it happens, namely that is when the vorticity is everywhere 0. So the other interesting case is when they're parallel, but the vorticity is not everywhere 0. Okay, so maybe I'll skip this. Okay, so this is the Beltrami case. So vorticity being a constant multiple of u. You could also make this a variable multiple, but yeah. So in the results it's constant. Okay, so then we can consider steady water waves on Beltrami flows. So this is when you replace Laplace's equation for the velocity potential with these two equations instead for the velocity field. So this is just saying the condition that the curl is proportional to or collinear to the velocity. And then this is the divergence freeze condition. So it turns out again that these two, so it's not Laplace's equation, but still this is a nice elliptic problem. So you can, even though you don't have a velocity potential, you can use much of the same techniques. Okay, so what are these strange waves? So I mean, in the irrotational case, we're essentially bifurcating from uniform flows. So what is the analog here in the Beltrami case? So the analog is that you have solutions which are uniform for each vertical position. So, but the direction varies with depth. So they look something like this. So we have a two-parameter family of such solutions. Okay, and so these are the waves which we bifurcate off. And so, okay, I think I'll skip this. So, well, okay, so we look for doubly periodic solutions again, and we have to add some sort of normalizing conditions, this integral condition essentially. Okay, and so a difference compared to the irrotational case is that we no longer have this symmetry in both x and y individually. But as I said before, there is this, you always have this symmetry in x and y combined. So this can be used to reduce the dimension of the kernel to 2, but not to 1. So you can't use bifurcation from a simple irem value. But you can still use this other approach, which I mentioned before, where you have sort of this two-dimensional bifurcation. So using two different parameters. Okay, so I'll skip this. So this is the result we have together with Evgeny Lucaro and the Douglas Svensson set. And so this is a bit technical, but essentially assuming that you have two solutions of the dispersion relation, which looks like this, and no other solutions, and then some other technical conditions. Under these assumptions, you can construct a two-parameter family of doubly periodic solutions, bifurcating from these flows I showed here. Okay. And so essentially this is doubly, well, bifurcation from a double eigenvalue where you use C1 and C2 as parameters. So you get sort of bifurcation surfaces instead of curves. Okay, and we're currently looking into other things like fully localized solitary waves and also into, large, well, numerical computation of large amplitude solutions. Okay, so I think I'll have to skip the rest. So this is, let me just say something very brief about that. So this is the one result I have with vorticity. So this is this kind of special situation where you still have a sort of elliptic free boundary problem. The other result I wanted to mention is work in progress together with Christopher Warholm and Douglas Svensson-Seth, which is for nearly irrotational solutions. So these are solutions which, well, okay, so they sort of bifurcate from irrotational solutions, so uniform flows, but the vorticity is not zero. And so these are in the other situation I mentioned, if we go back to Arnold's result, where the Bernoulli function is not constant. And this means that, so you have this sort of a foliation of the domain into sort of invariant sets, invariant surfaces. And to construct these solutions, we used an idea from by Lortz from, well, so not that well-known paper in German for magnetohydrostatic equilibria. So the idea is to use symmetry, which means that all of the streamlines will actually be periodic. So in general, if you have this sort of situation where you have a non-constant Bernoulli function, so you have these invariant surfaces, but the sort of the flow, or I mean the streamlines will sort of be quasi-periodic or sort of dense on these surfaces. And so that's a much more difficult problem. Okay, so anyway, so what we're doing in work in progress is constructing solutions which are close to irrotational, and the problem is not really an elliptic free boundary problem. So there is a sort of elliptic hyperbolic, and this causes a lot of problems. So you have to deal with sort of, whenever you take Fréchet derivatives, you lose some regularity. And yeah, so this is something you have to deal with. Fortunately, if you have surface tension, this is sort of enough to regain some regularity so that you can handle the problem. Maybe just finish with a recent thing I did after the last time I talked about this. Namely, I wanted to figure out what the Bernoulli surfaces actually look like in this case. So I mentioned that the Bernoulli constant is, sorry, the Bernoulli function is not constant. So this is a computation of the Bernoulli surfaces in sort of expanding in the amplitude. So this is something to, well, okay, let's say the first order expansion of the Bernoulli surfaces. And what's interesting about them is that neither the bottom nor the surface is a Bernoulli surface. So this is a contrast to the 2D case where both the bottom and the surface are Bernoulli surfaces. Okay, so, well, thank you for your attention, and sorry for taking too long.
No, it was just perfectly fine. Okay, thank you very much, Erik. So as per usual, we'll do the weird thing where I actually have to mute everyone in order to give you the right to unmute yourselves. Okay, now everyone is free to unmute yourselves. If you have a question, feel free to shout it out to Erik. Oh, and Erik, you're muted.
Yeah, I have a question. You said a lot, actually. It was there was a lot in a lot of different things you talked about. But one of the things you emphasized was doing the bifurcating from two different variables instead of bifurcation from a simple eigenvalue. So you use sort of a Lyapunov-Schmidt type of thing to reduce down to a low dimensional problem. Is that the tech?
Yeah, and yeah, so that's the technique, and then essentially, well, okay, so you need as many sort of parameters as the dimension of the kernel, essentially, and then it's just that the equations become more complicated if you have sort of 10 equations to solve instead of one. And so, but there are different. I mean, you can either do something like you do in the standard Kandor-Rabinowitz theorem. So essentially, you have to sort of factorize the equations and then use the implicit function theorem. So that's one way. So that's essentially what I did in the results of these Beltrami ways. But then you could imagine using other techniques like Craig and Nichols, where you use some variational technique, something like that. Or you could use topological. So they also use topological arguments, in fact. So. But so maybe one thing I think is interesting, which I didn't wanted to mention more open problems, but maybe one thing. I don't know of any sort of global theory where you bifurcate from sort of a two-dimensional kernel or high-dimensional kernel. I mean, sort of getting a global bifurcation surface. I mean, usually you find sort of global curves, but yeah. So I think it's a very difficult problem, but I don't know if you can say something meaningful, but I think it would be very interesting if you could.
Yes, it would. Thanks.
Other questions? I have a brief one. So you showed the picture of the sort of Beltrami flows that you're constructing the solutions for
Yep.
At the end. So what I didn't quite get is, are you constructing these solutions for sort of general Beltrami flows, or is it really just that specific family that kind of builds, that thing?
Yeah, it's that specific family. So we start off with that, and then we bifurcate.
I see.
So, I mean, otherwise you would have to, well, I mean, I'm sure you can do more, but I mean, somehow they have to fit the domain. So,
sure. Okay, yeah. That was exactly actually my question. So are there other known examples of nice Beltrami flows that fit in the domain in the way that you would want here?
Not that I know of. Yeah. So, I mean, so it would be interesting. I don't know if you can, if you go to higher amplitude, if you can get something looking more interesting, where you have this sort of knotted streamlines and things like that. That would be very interesting, I think.
Thank you. Other questions or comments? Okay, well, thanks a lot, Erik. Let's thank Erik again. And I would also like to say thank you to all of the other speakers who gave great talks during this thematic series. It's been a lot of fun, so thank you very much. I'm going to hit stop on the recording.